differentiation. So these are your common kind of differentiation functions. So you have polynomials, we have exponentials, we have circular functions, and we have logs. So all the stuff we've talked about so far. Importantly, lots of the formulas are in your bad notes, so that really saves you in exam 1 and kind of gives you a reminder of what to do. So these are all the formulas that you can kind of actually use. I think the important thing to kind of point out is you can do this without, like, this one's really helpful. This is kind of like a chain rule but already done for you, so that's really helpful to know. And this one also is a bit tricky because it actually turns into a kind of like, not a polynomial, but I guess it turns into a polynomial like thing, right? And these ones, the important thing to remember is this turns into sec, which is 1 over, or a over cos or whatever, 1 over cos squared. And this is negative while this is positive. Alright, so there's a couple of rules that we'll just chat about before we actually try to differentiate a function. So the first one is the product rule. Like the name suggests, it's used for products, so when a function is times by another function. How I like to describe it is I diff one, leave the other, diff the other, leave the one. Okay, and that's how I remember it in my brain. So what I do is essentially, if you want to set it out really nicely, what you can actually do is you can name these u and v and use the like Leibniz type notation. So you have u equals to x squared, v equals to x plus 3, and that way you can say du dx equals to 2x, and then dv dx equals to 1. And then you can kind of just put it, so if I diff one, leave the other, so x squared, and then diff the other, leave the 1, and then put times those together. And then you kind of just make sure everything's simplified, so you get 2x squared plus 6x plus x squared, which is just going to equal to 3x squared plus 6x, and then you just leave it. So diff the other, leave the 1, diff the 1, leave the other, or diff 1, leave the other, diff the other, leave the 1. Essentially, you can also set it up like this and just do like a crisscross match as well. Cool. Alright, chain rule, it's used for our composite function, so our f of g of x. So it won't be written as a composite function, it will just say what it is, so g of x equals blah. But you'll note that two different functions are combined together in it. So what you need to do is just diff the inside, keep the outside. So diff the inside, diff the inside, diff the outside, keep the inside. So what you do is you leave the inside, pretend that it's inert, and you diff the outside, but then you can't just really do that because that means you're not really considering this a function, so you just diff whatever's on the inside as well. So you just need to care for both parts, so you care part 1, part 2. Cool. And I guess for this one, once again, you can also do like a u and v type situation as well if you want. Okay, so let's go through this one together. So we have cos e to the 2x, and hopefully you're saying that this one will be equivalent to your chain rule because you can kind of see that it's a composite function. So importantly, we kind of need to consider that. So if we look at this, we see that it's y equals to cos e to negative 2x. So we know that this is the inside and this is the outside, right? And I guess another way you can write, so if we have f of g of x, another way to write the derivative of that is f dash g of x and then g dash of x. So what we can do here is e to the power of negative 2x, that's just going to be negative 2 e to the power of negative 2x, and either x I really like because you just basically put whatever's in front of the x out the front. So that's diffing the inside. Now we diff the outside, keeping the inside the same. So cos diffs to negative sine, and that we just keep e to the negative 2x on the inside. Right. So if we kind of simplify and just connect all of those together, we'll just get 2 sine e to the power of negative 2x e to the power of negative 2, e to the power, so 2 sine e to the power of negative 2x. That's all we need. Oopsies, sorry. Negative 2 e to the power of 2x sine e to the power of negative 2x. So it should be negative here. Cool. So yeah, just write it all together and just kind of simplify and clean it up a little. Okie dokie. Alright. So like I said, logs are a bit trickier, and this rule is super duper 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 useful. So just make sure to kind of make use of that and have that in your formula sheet or bound notes in some form or some matter or form essentially. So you want to have this in your bound notes because this like is useful for differentiation, yes, but it's super duper useful for integration, especially because sometimes you'll have something like they'll be like integrate tan of x dx, right? And there's no like formula for integrating tan. So what you actually have to do is split it up into sine x over cos x, right? So this is anti-differentiation. And then once you do that, you can kind of see that it's basically in this form and you can just manipulate it from there. So when we have f of x, essentially we just need to go f dash of x over f of x. And that also makes our differentiation easier as well because the chain rule, remember, it's diff the inside and then keep the outside with the inside being the same. So it would just be f dash of x. And then because log ex is just 1 over f of x, it just works out to be simplified into this form. Alrighty. So let's give that a try now. So if fx equals to if fx equals to log ex cubed, find f dash x. So what that's going to equal to here is we know that this inside is our hx or our fx from before. So what we're going to do is diff the inside, which is 2x squared, and we're going to put that over the outside, which is just x cubed, which essentially we can kind of see that cancels that, so it's just 2 over x. So that makes it really nice, simple, clean. Alright, let's talk a bit about stationary points. So those are the rules itself and how we actually derive and do all of that stuff. So let's talk about how we actually can use our differentiation. So when we derive something, what we're trying to find is the gradient of the function, right? So when we find the derivative, a synonymous for that is we're trying to find the gradient. So that kind of enables us to find stationary points, and the word stationary points kind of gives away what type of points there are. They're literally when they have zero gradient, so it's not moving, so that's when there's a zero gradient. So what we're going to do therefore is try and find when f dash of x or dy dx equals to 0, and we can solve for the x coordinate using that. There's 3 points at which we can kind of get a stationary point, and these are turning points, so local mins and local maxes, and stationary points of inflection. So those are the 3 points that we can actually get a stationary point at. No other point on the graph will really be a stationary point. So once we solve for stationary points, so once we solve f dash of x equaling to 0 or dy dx equaling to 0, we can then determine their nature. So there's kind of 2 ways to do this. We can either sketch the graph, which can be easy for some and can be more difficult for others, right? Because like for a cubic or something, we kind of know the general shape of it, so it's okay to graph. But for something which is a bit more funky, it's probably a bit gross to do. And in fact, you are probably finding the turning points and stuff to actually help you know what the shape of the graph looks like. So you can use something called like a gradient table if that doesn't work. Which is finding the gradient immediately before and after. We'll do both methods kind of here to talk about how it works and how we can use it together. So it wants us to find the stationary points of 2x cubed minus 3x squared minus 36x. And the first thing is we want to find what f dash x is. So even if you don't really know what's really going on, but you get the vibe that you'll have to do something with differentiation, just derive. You'll get at least 1 mark, because you've at least done the first step. So if we try and find what f dash of x here is, or more appropriately dy dx here, because everything's in terms of just y, it will just be 6x squared, so we took down the power, reduced the power by 1, minus 6x, so take down the power, reduced the power by 1, and then minus 36. Now, we're now going to try and find the stationary point, so that means that dy dx equals to 0. So we'll have 0 equals to 6x squared minus 6x minus 36. So what we're going to do is now we can just divide everything by 6, so we don't need as big numbers. So it'll just be x squared minus x minus 6. Cool. Now we can kind of factorize them into 2 brackets. So that's going to be x minus 3, x plus 2, right? So therefore we'll have x equals to 3 or x equals to negative 2. Alright, so now we need to determine the nature of these things. So we can kind of just have a go at determining the nature. So there's, like I said, there's 2 ways. There's really actually 3 ways. There's also something called the double derivative as well, which I guess the use of it's not encouraged in methods, and I wouldn't really use it in your SACs, but it should be fine to use it in your VCA exams. So just keep that in mind as a method as well. And it's essentially when you just find the second derivative and then you sub it in. We can just have a brief chat about that as well. But essentially what we can do here is we'll just kind of set it up. So we can just graph it actually instead. So we'll know that this graph approximately, I'll probably need to find the turning points and everything then. Okay, that's right. Let's try and find the points, like all of the turning points and stuff. So not the turning points, the x-intercepts. So if we subbed in 2 there, we would have gotten 16 minus 12. So that's negative 28. So that's not quite right. No, that's too big. Okay. What about 1? So that's 2 minus, no, that's definitely too big. What about negative 2? So that's going to give us negative 8 minus, no, that's too small. So then 3. So what I'm just doing is just the factor theorem for the polynomials. 3, so that's going to be 27. Negative 54. Negative 54 minus 27. Oh no, negative 54 minus 27, so negative 61, negative 81, and then that times by 3 would be 18, 108. Okay. If we had, if we were allowed to graph this on our calculator, just so we can make sure to get through all of the content, 2x cubed minus 3x squared minus 36x. Okay, so I guess one of the points would just be 0, right? It's a good point to take out. So it's points pass through 0, and then we have 2x squared minus 3x minus 36. And then we can do like quadratic formula on that. But we kind of know that the general shape is going to look like this, right? Because it's a positive cubic, so it's going to look something like this. And therefore we can tell that this is going to be the max and this is going to be the min immediately. So we're pretty happy. Like that's one of the ways you can do it. Another way you can do it is via the gradient table. So what you do is you just put in the points. And so I'll have negative 2 here and I'll have 3 here. And I like to sandwich this, so I have to find one less point. Just makes life easier. So this is x, this is f of x, and this is what the lines look like. So at negative 2, we should get 0, right? Because if we get negative 2, that's going to just equal to 24, and it should give us like the number that we need, right? Because we should get, so negative 24 plus 12 and then minus 36, so we'll get 0 here, 0 here. We can do 0 in the middle here, and then do negative 3, and then I would just do 4 here. Just 2 like simple numbers is better. So if we sub in 0 here, we'll get negative 36, which is smaller than 0, so it's going to go down. So we'll have 0, so these are flat lines. And then we'll have negative 3, so negative 3, so that's going to be 9 times 6, so that's 54, plus 18, so that's going to be 54, 64, and then 72, so 72, then minus 36, that's going to be positive 36, now that's going to be up. And then we're going to sub it in 4, so 4 squared is going to be 16, 16 times 3 is 48, so that's 96, so 96, then minus 24 is going to be 72. Once again, it's going to be 36 here, so it's going to go up as well, and we can kind of see down, down, down. So once again we get the local max and then local min as well. Cool. And then in terms of the second derivative, so f dash dash of x is going to just be equivalent to 12x minus 6. So if we sub in those 2 points, so negative 2, f dash dash of negative 2, that's going to give us negative 24, negative 30. So if that's smaller than 0, it's a local max. If it's bigger than 0, it's a local min. And if it's equivalent to 0, we don't really know, but it's a point of inflection of some sort. Cool. All right. Optimization problems are essentially like an application-y type of question. And essentially what they just want you to do is just maximize or minimize the quantity of something. So there's a lot of applications which involve this. The main thing is that we really need to be careful about finding the absolute maximums and absolute mins rather than local maxes and local mins. So what you essentially want to look for is 1, the local maxes and local mins, and then 2, the endpoints. So 1, local max, local mins, 2, endpoints. And that's really only the points you need to check. Okay, cool. So another application that you can have here is finding the angles between something. So it's just remember the relationship that because we're finding the gradient, and gradient is rise over run, i.e. tan. So if we just equate the gradient, so when we find the gradient by subbing in values into the function, we'll get m, and then we can just equate that to tan, and then from that, what we'll actually get is just the gradient of the function, which will kind of make our life easier, right? So we can just find it from there. Alright, so this one, find the angle from the positive direction of the x-axis to the tangent. Remember, it is always the angle from the positive direction of the x-axis. So whenever you find an angle, whenever you do a tangent, always from the positive direction x-axis. That's because the unit circle, remember, goes that way. Alright, so at negative 1, and you can see measured in anti-clockwise direction because of the unit circle. So f dash of negative 1 is going to be equivalent to negative 1 over root 1 minus 2 times negative 1, right? So that's going to be negative 1 over root 1 plus 3. 1 plus 2. Got ahead of myself. So that's negative 1 over root 3. Now, we're going to equate that to tan theta. And if we draw our little triangle here, we have root 3, we have 1, and we have 2. If we want 1 over root 3, that's going to equal to our pi and 6 because we want kind of our opposite over our adjacent, and it's going to be negative as well, which means that it has to be in this quadrant, right? Because we're talking about angles up to 180, and this is, I guess, a special circumstance where you use degrees. I feel like this is used more commonly here. So it's going to be in this quadrant, and it's going to be pi and 6, or otherwise known as 30 degrees. Therefore, this angle should be 120 degrees, right? So we're going to say theta is therefore going to be 120 degrees. Cool. All right. So then what we can kind of do here is we want to consider what else we want to do. Oh, sorry, not 120 degrees. What am I talking about? That's pi on. This is 30 degrees, so 150 degrees. Sorry, because it's pi on 3, meaning pi on 6, not pi on 3. So it's 150 degrees. So then what we can kind of consider here is so it will be essentially just be if we pretend that was a function, right? At that point, the gradient of the tangent would be going like this. So we'd have an angle kind of coming from there. Alright, in terms of angles between lines, you can use this compound angle formula used in Spech. Alternatively, you can also just look at the picture as well, but this formula is helpful. So it's m1 minus m2 plus m1, m1, m2. Cool. So if we try and find the acute angle between these two lines, so we'll have 1/3, which kind of passes through here, right? And then we'll have 2x negative 1. So, no, sorry, that should be going up. So it should be going, so we'll have 1/3, so it'll kind of be 1/3, 3, and it'll kind of vaguely look like this, and then we'll have 2x and negative 1. We'll have something looking more like this. That's probably not very to scale, but so they're essentially asking us to find the angle here, right? And we know we can find the angle here and the angle here. So if we look at this, we can either find these angles separately and then kind of use that, or we can use the formula from before. So if we use the formula from before, so tan theta would equal to so it was equivalent to m1 minus m2. So it kind of doesn't I would say it like it doesn't really matter which one you consider M1 and M2 because eventually you are going to end up with the same angle. But I guess you can kind of tell. So if you end up with an obtuse angle here, you kind of just do have to use logic to which angle you really pick. So I would say we have to try and keep it positive, especially if we're trying to find, so it tells you it finds a cute angle. So like you can kind of use your logic here. I'm going to go with 2 minus 1/3 just because I think that's going to give me my positive result. So then it's 1 minus my M1 times my M2. So that's going to just be, 1 plus my M1 plus my M2. So what I'm going to get here is that it's just going to be that it's 2 times 1/3. So that's going to equal to 2/3 over 5/3, right? So alternatively, that's going to equal to 2 over 5. So my theta is just going to equal to tan inverse 2 over 5, right? So this formula can be really useful in that manner.